In this video, I'll be going over the Fundamental Theorem of Calculus. And the Fundamental Theorem of Calculus deals with evaluating definite integrals. Now, previously what we've seen, in order to evaluate a definite integral, we have used either a Riemann sum, or we've used some possible geometric formulas. So if we had an area that came out to a triangle, for example, we could evaluate that definite integral using a formula for a triangle. But both of these, were pretty tedious or cumbersome, and so it'd be nice to have a cleaner, faster way to evaluate definite integrals, and that's what the fundamental theorem does for us. So the fundamental theorem of calculus is used to evaluate definite integrals. And what it does is it establishes a relationship, between integrals, and derivatives. So the fundamental theorem of calculus can be broken down into two parts. We have, if f of x is continuous over an interval a to b, with x between a and b, and the function f of x defined by this right here, so capital F of x is equal to the integral from a to x of f of t dt, then what the fundamental theorem of calculus tells us is that capital F prime of x is equal to f of x over the interval a to b. Now what is this saying? This is saying that if we have some function equal to a definite integral like this, where we have a constant, let's label this, so a is a constant, and x is, a function of x. To evaluate this integral on the right-hand side, all we do is we take the function f of t, and we're going to input whatever this function is that we have in the upper bound. So one way of thinking about this is the derivative of the left-hand side is equal to the derivative of the right-hand side. Or in other words, d dx of capital F of x is equal to d dx of that integral. Okay, so in other words, what this is saying is if we differentiate both the left-hand side and the right-hand side, that is going to undo this integral on the right-hand side. That'll give us the inside function as a function of whatever that upper bound is. Okay, and then what this also shows, the fundamental theorem of calculus also shows that any continuous function has an antiderivative. Okay, now this all might seem pretty confusing, but in practice this is actually quite straightforward. So let's look at one or two examples. So this example says, use the fundamental theorem of calculus, part 1, to find g prime of x of this function. G of x is equal to the integral of, or the integral from 1 to x of 1 over t cubed plus 1 dt. So what the fundamental theorem of calculus is telling us is that if we take the derivative of both sides, so d dx, okay, so on the left-hand side that leaves us with g prime of x. The derivative of the right-hand side is just the integrand, so 1 over t cubed plus 1 but we're going to evaluate that at this upper bound. So what we're going to have on the right hand side is 1 over x cubed plus 1, and that is it. So it's actually pretty sweet, you know. I mean, before, to evaluate something like this, again, we're going to have to use Riemann sums or try to use some geometric formula, but the fundamental theorem of calculus is much more straightforward in how we can evaluate a definite integral like this. Okay, let's look at a second example. Evaluate the integral from x squared to 1 of t to the fourth plus 1 over t squared plus 1 dt. Now, the fundamental theorem of calculus tells us that we need this upper bound to be a function of x, and we need the lower bound to be a constant. So one of our rules or properties of definite integrals is that we can reverse the limits of integration. So we can flip the bounds here. So the lower bound and the upper bound switch positions. And what that does is that negates whatever the integrand was. So now we have the bounds and how we want them. We have the lower bound as the constant, so we have a constant down here, which is what we want, and then we have a function of x, or some other variable besides t in the upper bound. Alright, so what we can also do is, with definite integrals, or any integral, any negative sign out here can be taken out of the integral, so we're going to have negative the integral from 1 to x squared of t to the fourth plus 1 divided by t squared plus 1 dt. Okay, and now to evaluate this, we're going to say negative of, so I'm going to input this function in for wherever we have the t. So this will be x squared raised to the fourth plus 1 divided by x squared squared plus 1. And what we need to do here is, because x squared, we need to apply the chain rule here. So we're taking the derivative of both of this entire expression. In a sense, we're undoing that integral, so that means we're taking the derivative. And so when we do that, we need to take the chain rule, or apply the chain rule to x squared. So we need to say d dx of x squared. And this is just applying the chain rule here. Okay, so doing so, we're going to say negative of x to the 8th plus 1 divided by x to the 4th plus 1 times the derivative of x squared is just 2x. So we can leave it like that, but I would probably simplify this to negative 2x times x to the 8th plus 1 divided by x to the 4th plus 1. And that does it for us. Alright, and one last example that uses part 1 of the fundamental theorem of calculus. We have the integral from square root of x to 3x of t squared plus sine of 1 plus t squared dt. Now what we'll notice here is that the limits of integration are both functions in x. And so, you know, what we see here is that our lower bound is square root of x, our upper bound is 3x. Now I don't know what the graph of this function looks like, but it doesn't really matter. Let's say it's something like this. So we want to integrate from square root of x to 3x. Now, in order to apply part 1 of the fundamental theorem of calculus, we need a constant down here in this lower bound. So what we can do is we can say, well, let's just split this up at c, where c is some constant, and I'm going to rewrite this integral as two integrals getting added together. So it'll be this left-hand integral and then this right-hand integral getting added together. Okay, so the left-hand integral, we're going to say square root of x up to c of t squared sine of 1 plus t squared dt plus, and then the integral on the right part is going to be from c to 3x of that same integral, the same function or the same integrand. So t squared of sine 1 plus t squared dt. Okay, so the integral on the right, that looks good. We have a constant as the lower bound and a function in x as the upper bound. The function on the left, though, we're going to need to swap the upper and lower bound here. So I'm going to rewrite that as negative integral from c to square root of x, and then this will be t squared sine of 1 plus t squared dt plus that integral on the right. So this is c to 3x t squared sine of 1 plus t squared dt. All right, and then why don't you go ahead and see if you can evaluate each of these. Why don't you pause the video and see if you can do that before I show it. Okay, so the integral on the left, we're going to say, I need some more space, we're going to say negative of, so wherever I have a t here, I'm going to input square root of x, so it'll be square root of x squared sine of 1 plus square root of x getting squared. Then I need to apply the chain rule, so the derivative of the square root of x, which is just 1 over negative 2 root x. Okay, and then for the integral on the right, we're going to say plus. So now I'm going to input 3x for t, so 3x squared sine of 1 plus 3x squared, and then times the derivative of 3x is a 3 here. Okay, so simplifying some stuff here. Let's see, this negative and this negative will cancel. And then, let's see, so in the numerator I have square root of x squared, so that's just x sine of 1 plus x. And then in the denominator we have 2 square root of x plus 3x squared. Well, 3 squared is 9, and then I have another 3 back here, so that's 27 x squared sine of 1 plus 3x quantity squared is 9x squared. So that'll do it for us. So now we'll move on to the second part of the Fundamental Theorem of Calculus, which says, suppose lowercase f of x is a continuous function on the interval a to b, and also suppose that capital F of x is any antiderivative of that function, then the definite integral from a to b of f of x dx is equal to the antiderivative, which is capital F, evaluated at b, minus the antiderivative of lowercase f evaluated at a. In other words, this is saying, take the antiderivative of f of x. Let me write that in a different color. Take the antiderivative of f of x, evaluated at b, and then subtract that from the antiderivative evaluated at a. So let's look at an example that helps to illustrate this. And this is actually even more handy than part 1, because in part 1 we had the upper bound as a function in terms of x. Now we have two constants that are the bounds of integration. So we're going to end up actually with an exact value, an exact numerical value of what this definite integral is equal to. Okay, so we'll go step by step on this one. The first thing we want to do is find the antiderivative of this function. So we're going to denote the antiderivative as capital F of x, and we'll say our original function is lowercase f of x. So capital F of x is the antiderivative of x squared plus 1, and that antiderivative is, if you recall from a previous video, using the power rule for integrals, we're going to raise the power by 1, and then we divide by that new power. And then the antiderivative of a constant is that constant times whatever our variable of integration is, which in this case is x. So 1 times x, just x. Okay, so we've got our antiderivative, and then what we want to do is we want to evaluate that at the bounds of integration, which are 0 and 2. So based on what we have here, we're going to say f of b, or capital F of b, so we're going to say f of 2 minus f of 0, which is going to be 2 cubed divided by 3 plus 2. And then we're going to subtract capital F of 0. So 0 cubed divided by 3 plus 0. Okay, so evaluating this, we're going to have 2 cubed is 8 over 3 plus 2. I'm going to rewrite that as 6 over 3 minus 0 plus 0 is just 0. So we get 14 over 3. So one way to think about what we just did with this definite integral is, well, if we have this function x squared plus 1, okay, so it looks something like that. And what we're doing is we're evaluating that from 0 up to 2, and we just found the area under the curve. Okay, so that area is 14 over 3. Now you might be thinking, well, I thought we needed to add a constant when we're finding an antiderivative, and that's true. But what you could see here is that if we added that constant to this and this, it would end up canceling out. So if I had plus c in here, plus c in here, well, I'd have a positive c in the first expression, or the first set of parentheses, and then this minus sign would make the c negative. So the c's would cancel. So you can write that out. I think it's you'll get tired of doing that because it'll always cancel. So you don't actually need to write that constant c when we're evaluating definite integrals. When we're evaluating indefinite integrals, it is vital that you put that. Okay, let's look at another example. We have the integral from -2 to +2 of t squared minus 4 dt. So we'll just go step by step again. Let's say that this is our function f of t, or lowercase f of t. And we want to find the antiderivative of that, which is going to be capital F of t. So again, using the power rule, we're going to say t cubed over 3 minus 4t. Okay, and then we want to evaluate that at 2 and -2. So what we want to do is we want to say capital F of 2 minus capital F of -2. So that's one way we could do this. Another way we could write this is, well, we have the same antiderivative, 2 cubed over 3 minus 4t. Now when we want to evaluate this, the shorthand way is by saying from -2 to 2. So we write the limits of integration like this. So what we do is we evaluate the antiderivative at 2, and then we evaluate the antiderivative at -2, and we subtract those. So we're going to say 2 to the third over 8, over 3 minus 4 times 2. And then we're going to subtract the antiderivative evaluated at -2. So -2 cubed divided by 3 minus 4 times -2. Now we need to be very careful when we're doing, evaluating, or I guess inputting the limits of integration, because it's really easy to lose track of this negative sign and to forget to put parentheses around everything. So we need to make sure that we're subtracting the entire expression. Okay, so from here it's just simple arithmetic. We end up with 8/3 minus 8 minus negative 2 cubed is negative 8/3 plus 8. So I'm going to have 8/3 minus negative 8/3. So 8/3 plus 8/3 is 16/3. Negative 8 minus positive 8, so minus 16 here. And if we get a common denominator and combine those, we're going to get negative 32 over 3. So again, what does this look like? Well, we have a parabola with a y-intercept down at negative 4, so it's going to look something like this. When t is 2, so it looks like it's hitting at 2 and negative 2. So what we found is this area in here. And a special note, I mean, an integral can have a negative sign because an integral doesn't only mean area. So if we talk about the area, we could say it's 32 over 3 because it doesn't really make sense to have a negative area. But if we're evaluating an integral, it can be signed. So definite integrals can be negative. Okay, so we just need to really understand what we're doing. That integral can be a negative value. And this negative just means that there is more area under the x-axis than above the x-axis. So that's how we should be interpreting a negative value as our definite integral. All right, let's look at just a couple more here. So this one's similar to what we've seen. We have a definite integral from 1 to 9 of x minus 1 over the square root of x dx. We will see some ways that we can evaluate this without the power rule, but let's use the power rule here. And what I'm going to do is I'm going to split this fraction into two fractions. So we're going to say the integral from 1 to 9 of x over square root of x dx minus the integral from, from 1 to 9 of x over, we want 1 over square root of x dx. So what I'm going to do with all of these, with these square roots, I'm going to write the exponent. I'm going to write these functions instead of in radical notation. I'm going to use exponents. So from 1 to 9, I have x over square root of x. So that's like x squared over x to the, x to the first divided by x to the 1/2. So 1 minus 1/2 is positive 1/2. So x to the 1/2 dx minus from 1 to 9. Now I have this is x to the 1/2. So if I bring it upstairs, I'm going to have x to the negative 1/2 dx. Okay, so I think that'll make our life easier. Now we can pretty easily apply the power rule. So x to the 1/2, so I raise the 1/2 by 1, so this is x to the 3/2 divided by 3/2 minus the integral from 1 to 9. Negative 1/2 plus 1 is going to be x to the 1/2 divided by 1/2. And let me just clean these up a little. This will be, actually, what am I doing? We don't need to write this anymore. We've already taken the integral. So what I should write is from 1 to 9 here. getting a little carried away with my integration symbol. So I'm going to simplify each of these fractions before I evaluate. So this will be 2x to the 3 halves over 3, evaluated from 1 to 9, minus 2x to the 1 half, evaluated from 1 to 9. Okay, so our first evaluation from 1 to 9, I'll have 2. Now x raised to the 3 halves, so that's the square root. I'm inputting 9 there. So that'll be 9. Square root of 9 is 3. 3 to the third power is 27. Divided by 3 minus 2 times 1 raised to the 3 halves. Well, 1 to the 3 halves is just 1. Times 2 is 2. Divided by 3. Minus, we're going to have 2 times 9 to the 1 half. So the square root of 9 is 3. So this will be 2 times 3 is 6. And then minus 2, 1 to the 1 half. 1 to the 1 half is 1, times 2 is 2. Okay, so that's what we end up with. Kind of running out of room, but I'm going to have minus 4 for this fraction. And then this is 54 over 3 minus 2 over 3, which is, let me write this over here. This is 54 over 3 minus 2 over 3. So that's, 54 over 3 is 18 minus 2/3. Maybe I should keep that as 54 over 3. So 52 over 3. 52 over 3 minus 4 is just 12 over 3. So 40 over 3 is what we end up with. We'll do one last example. It says, James and Kathy are running a race on a long straight track, and whoever runs farther after 5 seconds wins. If James's velocity is j of t is equal to 5 plus 2t, and Kathy's velocity is k of t equals 10 plus cosine of pi over 2 times t, who will win? So what we need to do is whoever is going to win has run farther after 5 seconds. So the functions we have represent velocity. So because these represent velocity, if we find the antiderivative of each of these, that will tell us the position. And what we want to know is what's the position, the change in position from for the first 5 seconds. In other words, from 0 to 5. So for James, from 0 to 5 seconds, we want to find the antiderivative of j of t. And then for Kathy, we're going to do the same thing. Okay, so all we're going to do is we're going to evaluate each of these definite integrals for the particular function, and then see which value gives us, which value is greater. So I'll set these up. We'll say 0 to 5 for James, which is 5 plus 2t dt. That'll be 5t plus 2t squared over 2 using the power rule. So those 2's can cancel out. That's going to be from 0 to 5. So we have 5 times 5 is 25, plus 5 squared is 25, minus, evaluating everything at 0. So the second set of parentheses is just 0, so we have 50 over here. So James has gone 50, and I don't know if we even have a unit, but I guess it could be feet or whatever, but feet makes sense, I guess. And then let's look at Kathy's distance. So from 0 to 5 of 10 plus cosine pi over 2t dt. So we're going to take the antiderivative of that inside part. So 10, we'll have 10t plus, the antiderivative of cosine is sine. And then we keep the inside or the argument the same. So if you want to check that, let's say, what's the derivative of sine of pi over 2t. Well, the derivative of sine is cosine, and we're going to have to use the chain rule here to find the derivative. So what we do is we take the derivative of the inside part, which is pi over 2. Now this doesn't quite look exactly like what we have here. So what it looks like is we have an extra pi over 2 lurking in the back. So what we need to do is, in order to account for that pi over 2, is if we divide this by pi over 2. So it's kind of like undoing the chain rule. We're going to divide by what we were multiplying by when we were taking the derivative. We were multiplying by the derivative of this inside part. That was the chain rule. So when we do the antiderivative, we're going to divide by that inside part. Okay, so let's evaluate that from 0 to 5. So we're going to end up with 10 times 5 is 50 plus sine of pi over 2 times t. So this will be sine of 5 pi over 2 divided by pi over 2. And then we're going to subtract that. Let me get some more space here. We'll subtract 10 times 0 plus sine of pi over 2 times 0 divided by pi over 2. Okay, so what we have here, well, 50 plus sine of 5 pi over 2, that's the same as sine of pi over 2. Sine of pi over 2 is 1. So in the numerator is equal to 1. And then I'm dividing by pi over 2, which is the same as 1 times 2 over pi. So this will be plus 2 over pi. And then here, this is 0. Sine of pi over 2 times 0, so sine of 0 is just 0. So this whole fraction becomes 0. So I'm subtracting 0 back here. So the whole integral is equal to 50 plus 2 over pi. So how does that compare to 50? Well, it's bigger. So it looks like Kathy has gone 2 pi, again, if this is feet, she's gone 2 over pi feet more than James in the first 5 seconds of this race.